36B uses NBS in order to activate an allylic position, either here or here. This works by delivering bromine at really small concentrations after you do the first initiation. So the first initiation looks like this. We take off the electrons from this bond and split them evenly between the bromine and the succinimide. When we do that, we end up with an extra stable succinimide style radical because this is stabilized in resonance. And of course, we also have a bromine radical. The bromine radical will abstract the most reactive hydrogen, the one that's going to leave behind the most stable radical. In this molecule, we have the ability to stabilize by this double bond through resonance. So if we pulled off something here or here, we'd be able to stabilize that better. If we pull off here, we can actually pull off a hydrogen. Here there's no hydrogens to pull off, so we really just have this hydrogen or the other hydrogen at the same location that can react with a bromine radical. So we're going to have a bimolecular homolytic substitution, which then gives us this radical at this position. Now the interesting thing is that that radical doesn't just stay at that position because it is resonance stabilized. So of course we have this exactly as it's drawn, but we also have the resonance form where we have the radical up here and then the double bond down here. So these are two different resonance forms. This is relatively stable, but we form an HBr, right? So the HBr is also present. We have this relatively stable radical, but we also have an HBr. The HBr can react with an additional NBS So this set of electrons, or the one on the bottom, can pick up an acidic proton, have bromine as a leaving group, Br minus. That forces us to tautomerize. We end up having now a nitrogen that's double bound to this OH, and then it's still connected to this Br. When this happens, this nitrogen is positively charged. It's pulling electrons more towards it than it otherwise would. That actually makes this bromine electrophilic bromine. It really wants to interact with another bromine, and we created a negatively charged bromine here. So we're going to take this, and we're going to be able to take the extra negative charge on this bromine and react it with here, and kick these electrons back off to make succinimide. That gives us a small amount of Br2 that's always present in solution. Anytime we have some acid which starts from the first step, then the NBS is going to slowly release Br2. That means we'll have Br2 present, and that's going to be what's most likely to actually react with this via propagation step. I should draw that separately. So now we're going to have a homolytic substitution where this radical or this radical will kick into the bromine and kick out another bromide radical that can continue to react. When we look at this first step right here, we see that we have either this position or this position. This position is slightly more stable because we have stabilization through hyperconjugation. And so this one is going to be a larger portion of the resonance contribution, and so this is going to be the one that leads to the major product. So the last piece that we'll see here is a bromine forming on this position. So this is our major product. A bromine at that position would be the minor product.